Welcome to a video about graph theory. The origins of graph theory come from the 1700s when we look at a story about a mathematician named Leonhard Euler, a Swiss mathematician, who became interested in a very famous problem, the Königsberg Bridge problem. So the idea was that there was this city, then in Prussia, but now in Russia, which was set on both sides of a river, and it had these two large islands, and I'll leave the pronunciation of those off. They were connected to each other by these 7 bridges. And so this problem was a bit of a legend in the city was, is there a way to devise a walk through the city that would cross each of the bridges once and only once? So you want to try to make this walk so that you don't repeat any of those. And this is a little bit of a layout of the city so you can kind of get a sense of what's going on. It's a little tough to see the bridges, so I'll highlight those for you. Let's count them. There's 1, 2, 3, 4, 5, 6, and 7. So the idea was, can you navigate this so that you cross each bridge once and only once? Now, I'll just play pretend here. I'm going to put a little person in the bottom right-hand corner of the screen. Let me try to draw a route that maybe this person could take. Maybe they'll cross this bridge right here, and they'll go up here and cross over this bridge, and then maybe cross down through this bridge, and then up over here. And then what they find out is they're kind of stuck up at the top here, but they have not yet crossed this one bridge to the right. Now, unfortunately, there's no way to get there from where the man's at without crossing one of the bridges twice. Like, for example, he could go back over this bridge and through, but then that would break the riddle, which is you don't want to cross a bridge twice. So Euler was fascinated by this problem and tried to solve it. And he kind of solved it by realizing that there was no solution. But what came out of this was a very fascinating facet of mathematics. And I want to point that out in this picture above in the middle of the screen that you see. So what you do is you start with a rendering of a map, like the real picture. And then you can say, well, what's really important about this map? Well, what's really important is that there's these different pieces of land. In this case, remember, there was 2 islands, right? There's an island here and then an island here, separated from each other, and the mainland by bridges. So you actually have like these 4 chunks of land. You sort of have the north bank over here, you have the south bank, you have island number 1, and then you have island number 2. All right, so let's see. So what ends up being important is these 4 chunks of land, which Euler represented with dots, and then 7 connecting bridges. So maybe you can see how perhaps the North Island becomes maybe just this one dot, right? So this chunk of land becomes a single dot, and then the South becomes a single dot. The island number 1 becomes a single dot, right? I'll just call this island 1 over here, and this is island. I'm using I for island number 2. And then the lines connecting them are the bridges, right? Notice that there's 5 bridges that come into island number 1. So you can see there's 1, 2, 3, 4, 5, and then you can see their connections go to these spots. So it's an abstraction of a real picture. Okay, we're going to call this a map. The bridges of Königsberg problem is an example of what we call a routing problem. You're trying to build a route. Now, throughout this unit, as we look at graph theory, this is going to be a continuing theme. And so these are some real life examples of routing problems. How does the UPS driver make his route, right? How does the garbage collection route work? What's the difference between the two? How about an airline traveler? What about mail delivery? What about a walking route? And there's many other routes. And these routes may seem the same, but they're actually quite a bit different. I'll give you one example before we head into the last part of this video. A UPS driver, like number 1, a UPS driver, if you're familiar with UPS, they have a bunch of stops, but they don't stop at every house. So they're developing a route based on a certain number of stops. However, mail delivery, and it depends, but if you think of a traditional mail delivery where mail is delivered in a mailbox at the front of the street, the route actually is to go to every house and go down every street on both sides of the street. Whereas maybe number 2, a garbage collector, they may go down one side of the street, or they may go down the alley. It all depends on the situation. And so there's many different types of routes, and Euler's work helped us to make inroads into this. So here's a big takeaway. This is what we're supposed to learn. The physical map doesn't matter when you're developing these kinds of connections. It doesn't matter. What matters mathematically is just a list of which the regions are connected by the bridges in the original problem. So this is a whole new branch of mathematics that we call graph theory. Now below is something, is a picture of a bunch of different kinds of maps. You can see that there are a lot of connections between these different points or vertices, right? So if we take a look at the first picture, right, we have A is connected by, I'm going to call it an edge to B, like there's a connection there, but A is also connected to C and A is also connected to E. There's three ways to get from A to these other spots. Well, if you look at the next map to the right, this next one in the middle here, it's the same exact map, just with different lettering. So we consider that to be an equivalent map. Now, if you look on the far right, although things are curvy and look a little crazy, the connections are still the same, right? This one point here is still connected three ways, right? And even if you look at the previous picture, A is connected to B, and this map, A is still connected to B, just with a little curvy road, right? But what's important is the connections. And even in this flattened out map, it's kind of like a flattened out version of this box. We still have A connected with B, visible down there, and this top left-hand corner is still connected to three places. So these five figures all really represent, in graph theory, the same graph.